We are about to start calculus, differential calculus. And the first time I saw this, I was amazed. I could understand the basic concept. And when I looked at an example that was done for me, I couldn't believe how it worked. It's very, very fascinating. So this is the key class on the introduction of actual calculus itself. And we're going to start with a definition, and then I'll give you the example that really put me in a state of awe when I first saw it. Chapter C, the derivative. Remember, the derivative, as we talked about in our introductory chapter, you basically are taking a function, and I used an example of a trail going up a hill, and that graph of the elevation as you go out a distance x, horizontal distance, we want to make a derived graph which gives the slope at each point. That's called the derivative. Both are useful for hiking to know your altitude, your oxygen concentration levels in the air, and also how steep you're going to be climbing. So we start here with an arbitrary function. So here's your x-axis. X increases this way. This is your y-axis. And we'll look at a function here that does something like this. And we're going to be interested in the slope at this point. So that'll be x. And we're going to come over here. X plus delta x. Delta x is the change. So here, the delta x will be this distance. And what we're going to do is calculate the rise over the run. So here, if I go dot, 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 dot there, form a little rectangle here. This is your delta x, and this is your delta y, and your delta x here is the run. That's the distance along the x-axis, the run, and then we call this one here the rise. Now here, this looks like a good approximation, but in general, see if the slope here, went up a little bit more, so this would not be as good as an approximation. So really what we want is this measurement to be made when delta x is very small, delta y very small, because then you'll basically be describing the graph at that point, x here. Now this delta y, we can write this as, if we're going to write the function in general, the usual way like this, f of x, it's tradition to do that, then this would be f of x plus delta x. That would be taking you all the way up to the top, and then you would be subtracting this part here, which is the f of x. So f of x is right here, and if we were to do dot, dot, dot like that, then this one up at this height is f of x plus delta x. So we want to take that tall height and subtract the lower one, and that'll give you the change in the elevation. So we're ready to write our definition down. Our definition here for the derivative, we often just put a prime there, a derived function. based on this function will be, and we're going to say here the limit as delta x goes to 0. Here's the secret of calculus to do this kind of thing. This is new notation, perhaps. You haven't seen that. It's very, very cool. So we take the rise, which is the difference of the heights, and then we're going to divide by the run, which is delta x. And here's where it's fascinating, because you say you can't divide by 0. So like, what do? And that's the whole point of our study, to be able to work this out somehow. Now, in many books, you'll find delta x defined as h. They just use h, and I'll do that sometimes. I'll use h instead of delta x. You replace the delta x's with h's. But for this first example, and occasionally I like to use the delta x where everything's very explicitly shown. So here we go. Here is the mathematical steps, the calculation that really fascinated me, and I understood what calculus was in a basic way. And that would be taking a very simple function, x squared. So now we use x squared in the formula. So here's our formula. We need to have, for the derivative, as the limit of delta x goes to 0, we're going to need the function at x plus delta x. So that's going to be x plus delta x squared. That's the function at the higher place, although it doesn't have to always be higher. You can have negative slopes too, but in this case, it's going to be higher since we are dealing with x squared on the right side here. And we're going to subtract then x squared and divide by delta x. So that's using the formula. F of x is x squared, so you then put the x plus delta x in, square everything. Then the f of x, just the x squared, subtract. And the miracle that's going to occur here is that the delta x in the denominator is going to go away. Watch how this works. All right, so we want here for f prime, we're going to write down here our limit as delta x goes to 0, and now we're going to work out the top. Remember how we work out a binomial square. You square the first one, and then it's plus 2 times the product. That's the cross term. The cross terms, 2x times delta x, and then the last one squared, plus delta x. I'm going to go ahead and put that in parentheses like that, just to emphasize. They go together, and I'll even do it here. And then subtract x squared, and then we divide by delta x. And here's where the miracle starts to occur. X squared and x squared goes away, and everywhere else there's a delta x, at least one factor that we can divide out. So let's go to the next step. Okay, the limit as delta x goes to 0. What do we have left here? Well, we would have 2x times delta x plus the delta x squared. Now with these on the ends gone, I'm going to divide delta x into this first one, and I'll just get 2x. And to emphasize that the limit applies to the both terms, I'll put a parentheses. And then delta x goes into delta x squared, will just give us 1 delta x. And that's what we have here. Now notice that delta x can now go to 0, because we're not dividing by delta x anymore. So here, this is going to equal 2x. And that's our result. That's our slope function. So let's just look at this here. If we look at the parabola, we have the parabola here. This is, I'll write down here, this is y, and this is x, and this is x squared. So y equals x squared. And here we're going to give the derived function the derivative. So we can put here y prime, like that. And if you want, you can put the f2, you don't have to, but you can if you want to do it like many people do, like that. And this is still x. This is still x, it's just the vertical now has been replaced. Then you get y equal 2x would be something like this, where if you go over, say, 1, you would go up 2. Perhaps a little steeper than I drew it there. So just imagine that you're 1 step over, 2 steps up. So that means here, if you go 1 step over like this, then it's just you go 1 up because 1 squared is 1, but the slope here is 2. So the slope here would be 2. What I would like to do next is I'd like to check out something we already know. We know that a straight line, y equals mx plus b, has a constant slope. And the slope is, we know what the answer is, the slope is n. Well, would our master formula work for this? Let's try it. So f prime, we would want to go with the limit as delta x goes to 0. And now up here we put here the value of the function where the x plus delta x is inserted for x. So you would have this, and then subtract here, we would subtract the mx plus b, and we're going to divide all that by the delta x. This is our formula. I'll put some brackets there so that you know all that's in the middle. So this is simply using our definition, which is always good to emphasize. It's f of x plus delta x minus f of x, like this, divided by delta x. See, that's the key idea. That's what's in here. X plus delta x, when you put it in for the x here, you get m times the x plus delta x plus b, then minus just the function. So now we have cancellations occurring here also. This b here is going to go with this b. It's going to just cancel out. And you can see that this m times x will cancel this m times x. So the only thing I'm going to have left is going to be this m multiplied by the delta x. Everything else is gone. But then this is going to be quite easy to work out, because if you have just m times delta x and you're dividing by delta x, you're just going to get m, which is going to be the slope. And you can take the limit as delta x goes to 0. There's no delta x anymore, so I'll go ahead and write that step out here. Delta x goes to 0, but when I divide this out, I'm just going to get here, well, m delta x over delta x first, like that. And that's going to equal, and I'll still put the limit of delta x going to 0. This is m, but there's no delta x. Delta x can be anything here. So that's going to be m. And that's what we know to be the slope. So it works. Now we also did the case that's simple, even simpler, and that case was y equal to some constant c. That had 0 slope. y and x, say some constant c, it's just a constant wherever the x is, no matter what x it is, going to be the same elevation. Well, would that work with our formula? Well, let's go ahead and try it. And I like to emphasize what the formula is. It never hurts to write it down, it reinforces it, and I always encourage you to write things out. Not necessarily with me, but if you can, stop the video and kind of keep up with me. That probably would be the best way to do it. You always want to use your hands, write things out if possible. So this is going to be f of x plus delta x minus f of x, and we're going to divide by delta x, all right? I'm going to emphasize that that all goes together like this. So here, the f of x plus delta x is c, but the f of x is c. So when I substitute in for this, I'm going to have c, because it doesn't matter what the x is, it could be a constant. And this is going to be c. And then c minus c is going to be 0. And here, I would subtract that first so that I would get 0. Right. Delta x goes to 0. But now I have actually in here, before taking delta x to 0, because I don't want to deal with that being 0 in the denominator, when I subtract these, I got 0. So now delta x is gone. So here, this is going to be 0. Now see, I always recommend, and you really have to if you major in physics or engineering, to take calculus 3 semesters. And you take it with a mathematician. I highly recommend that, because they talk about these subtle things in more depth than I do. For example, they'll worry about when you take the limit of a sum here, is that the limit of each one separately? So, and they go into detail about things like that, which here we're not worrying about. It seems obvious, it makes sense that the limit of the quantity mx plus b would be the limit of the mx, and this kind of thing. But the mathematicians will deal with that more carefully, and I will list them later too, the limits. Like if you have a product or if you have a sum, I will list them. But in like the calculus classes, they'll actually prove those things. But something like that seems reasonable to a physicist, remember that we want to calculate things as quickly as we can and check them with nature, and nature is our guide. So if nature shows us the things we calculated measure correctly, then we're confident. And oftentimes, like in the study of quantum physics, mathematicians came later and made the subject more rigorous in terms of mathematical precision. So always bear that in mind, that different disciplines have different strengths and weaknesses, and they think differently. Our goal here in this basic calculus is just to emphasize the calculus that is needed as fundamental, a foundation for a physics major. And I can't, summarize too much. We don't have that much time. We're doing one course here, and if I look at some of these lectures I posted, they may be just 20 minutes or a half hour. I'm going through A to Z. So if you look at a whole semester, calculus 4 semester course, that's 4 hours. That's a lot more, you see, and 3 times that, because calculus 1, calculus 2, and calculus 3 then have a lot. See, if you do A to Z on Tuesday, Thursday mode, to get 3 hours, you would do 75 minutes. So you get the idea here that I'm doing a Tuesday, Thursday mode here, A through Z, with short lectures. And that would be like a 2-hour course or something maybe there. And if you have a calculus 4-hour course, there's 3 of them, you're basically looking at 12 hours instead of just like the 2. So just bear in mind that this is only the foundations and the basics that we're doing here to get you started. So assuming limit rules, like the limit of a sum is equal to the limit of each part added together, and the limit of a product would be each one separately. Then I can do for you ax squared. I'm just going to put an a in front of the x squared. So if we do that, we would have, say, for the derivative, like here, we have the limit of delta x going to 0, and we would have the function would be a times x plus delta x squared minus ax squared over delta x. And here, if we expand this out like we did before, we would have ax squared plus 2 ax delta x plus a times delta x squared minus ax squared. That would be up top. So ax squared would cancel ax squared, and the delta x would go into this first term, leaving the 2ax. The delta x would go into this term, and that would leave an a times delta x. So I'll put down here, you would have, this one would become 2ax. It's going to become that. All right. So then here you would have the limit of delta x going to 0 of 2ax plus a delta x. And here, with the laws of limits, where the limit of a sum is the limit of each one, and the product, you can think of this as the limit of the 2a times the limit of the x. So not worrying about that, we're going to just go 2ax. So we have a lot done here. If we have a little table to summarize our results in the book here, I have also the c times a function is then c times the derivative. If we come up here and say we have a new function that's g prime of x, where the g is going to be equal to c, a constant, times f, then I would have the limit of delta x going to 0 of, I would have a c in, well, these would be g of x plus delta x. I'll go ahead and write them out. G of x plus delta x minus g of x over delta x. But then the g would be this with the c in front. So that would give us the limit delta x going to 0 of c times f of x plus delta x minus c times f of x over delta x. And now bringing the c, the constant, out, you would have the c on the outside, and then you would have limit of delta x going to 0 of our basic definition involving just f of x. So that means that g derived function, the derivative, would be c times the derivative of f. And that's when g of x equals c times f of x. So that's another rule. So here in the book I summarized what we have done in this chapter. If you have f of x, here's your derivative, your slope function. If you put a c in front, it would be the constant times the same slope function that you had earlier. Then if you had the f of x, the function being a constant, you'd get 0. It's flat, no slope, or the slope is 0. And then if it's x, the slope, well, we did this one here, mx plus b, where the slope is m, but see, if you just pick x, that's b is equal to 0, then x would get you to 1. And then x squared, we did that's 2x. mx, we did that. So this is a nice little summary of important results that we'll be building on as we go. So I hope you enjoyed this introduction to calculus. This is the key lecture. It's like if you had a TV series and the first show or the first episode is the pilot episode, a very special episode. This is the very special episode that introduces the derivative and actually calculates sum for you. And now we're going to go on to take one function at a time from algebra class and take derivatives.